All right, so I'm Grant Grady. I'm the tutor for solid mechanics, and I figured I'd do an example problem here for you guys today. This is on angle of twist. So I came up with this problem myself. So what we're going to say is we have two pulleys, I guess you could say, or gears, if you want. Here, I'll restart that as well. So I'm Grant Graydon. I'm the tutor for solid mechanics, and I figured I'd go through an example problem for angle of twist for you guys today. So let's get started. So I came up with this example problem right here. And so in this problem, we're going to say that a torque is applied right here at this edge of 500 pound-inches, which is a lot of force. And we're going to be looking for the angle of twist at three different spots. We're going to be looking for it at A, looking for it at B, and looking for it at C. And our material is 6061 T6 aluminum, so our shear modulus is 3770 KSI, and 3000 KSI is our max shear stress. So, why don't we get started? I've dimensioned everything as well, so we can know what we need to know. And so let's get started. Let me move the camera over. All right, cool. So, this is our equation for max shear strain. We have a couple of different versions of it. This one uses C, with our angle of twist and length. There's also the version of tau max over our shear modulus. And then there's also TC times JG, or TC divided by JG, sorry. And we're going to be combining these so we can figure out our angle of twist. Now, for this first one, if you remember, C is the minimum distance from our central axis. So that means for a cylinder right in the middle. Our length is the length of the object. And then our angle of twist is if you had one end over here, you have one end over here at the bottom, and the other end at the top, and you twisted it, the twist in the middle is going to be our angle of twist. Kind of like a foam noodle that you might see in a swimming pool. I think that's a really good example of this. So, let's get started. We actually, let's see. So we're going to start with C phi L equal to TC over JG. And we're just equating. And we can do that because they're all equal to our max shear stress. So let's just start with our shear. Cancel out our C's. And now let us solve for phi. So phi is equal to TL over JG. Now, what do we know? Well, we know our torque is 500 pound-inches. We know our length. And we also know our polar moment of inertia. We also know our G value. So, I will start with calculating A. We're saying we're applying the torque right at this edge right here. That's what I was trying to show right here, is that right on this edge we're applying that torque. So we just got a length of 36 inches for A. So in this case, phi is equal to 500 pounds times inches multiplied by our length, which is 36 inches here. Divided by J, which is pi, I believe is pi over 4 times r to the 4th, which, if we look at our cross section here, we can see we have a diameter of 4 for these smaller pieces. So half of that, that's 2 to the power of 4 inches to the 4th, multiplied by 3770 times 10 to the 3rd, so that we can convert from KSI to PSI. So let's just do a quick little unit analysis. This is a great way to always make sure that you're on the right track. So we've got inches out, and this becomes the power of 2. And then if we look at the denominator here, what do we have? We have now inches squared multiplied by pounds per inch squared. And what's going to happen here? These inches cancel. These pounds cancel. And we're going to be left with a unitless number, which is exactly what we want because angle of twist is going to be in radians. Now, before I continue with my calculation, I admittedly want to double check. I will cut this out of the video before I upload it. Oh, I stand corrected. Okay. So, I don't have my book on hand, unfortunately. So, the polar moment of inertia. Down here. I'll just write up here. J is equal to pi over 32 times the diameter to the 4th. So that would be our 4 inches to the 4th times pi over 32. Now, I don't want to confuse myself, so I'm going to go ahead and erase this right here. I'm going to erase my unit analysis. I just wanted to double check it. It's a great way to make sure you're on the right track. Don't forget to raise this to the power of 4 for your polar moment of inertia. That to the power of 4 is referring to the inches, just because I pulled it out of there. And my calculator. I get phi equal to 0.000189 radians, which if I were to multiply that by 180 divided by pi, just out of curiosity, I'll get phi equal to about 0.01 degrees. So from this amount of torque, only 0.01 degrees over at this edge. Now, let's say rather than 500 pounds, we apply, let's say, 5,000. In that case, swapping that 500 out for 5,000, you get a 0.1. Reasonable, because it's just linear. Now, to solve for B and C, let's take a little shortcut. Now, this is a nice strategy if you're on a test or something with a massive time crunch. I don't know if I'd recommend this for homework because it's better to get practice, but here's a good way to save time is think about it. If we're trying to find for A, B, and C, what stays the same between A, B, and C? Well, color, that torque is going to stay the same, and our shear modulus will stay the same. But if you notice, when we look for B, this diameter is going to change from 4 inches to 12 inches. And when we look, our lengths are going to be changing. So 4 inches is going to be used for B, and then 4 plus 12 inches, so 16 inches will be used for C. But let's just rewrite this. I'm going to erase up here so I have more space. This, our derivation for this. So we can make 5 is equal to, just taking our constants and dividing them, we can say 500 pound-inch divided by 3770 psi. Multiplied by, we've taken out our torque, we've taken out our shear modulus. So multiplied by L over J. Just doing another unit analysis to make sure that we're keeping track of these things. And just it's good etiquette to do this. So we'll just do a quick little unit analysis up above. So pounds times inch multiplied by PSI is pounds per square inch, and it's 1 divided by PSI. So it's flipped. So pounds per square inch becomes inches squared per pound. Pounds cancel out. So that means this term right here should have units inch cubed. Which will make sense because this J, our polar moment of inertia, will have units of inch to the fourth. This has units of inch, so they'll cancel out like we want. But we practice to make sure our units are still doing okay and that it all makes logical sense. So now we can say 500 divided by, actually, typo, 3770 multiplied by 10 to the third. Forget that 10 to the third to convert from KSI to PSI. That means we can approximately say that our angle of twist is equal to 0.001326 times L over J. So now, let's solve for D. Zero, 1, 3, 2, 6, multiplied by our length, which is 4 inches, divided by pi over 32 times. For this one, we've got quite a large diameter, 12 inches, and it's all e to the power 4. It's going to give us a very, very small number. I'm going to write this in scientific notation so small. So that means our angle of twist for V is equal to 2.6 times 10 to the negative 7 radians. Or, once again, multiplying by 180 over pi to convert to degrees is also equal to 1.49 times 10 to the negative 5th degrees. Now, for C, it's really the same thing as for part A. The only major difference is the fact that we need to be aware of, if we're applying our torque right over here on this edge of this piece, it's not 12 inches away, but it's 4 plus 12, so 16 inches away. So I'm going to erase our answer for B. And just doing a sanity check, you should expect the angle of twist to be less than it is for A, because we've got the same diameter as A, same torque. The only difference is we're going for less length. So, C is equal to 0.0006 times 4 inches divided by pi and 32 times 4 inches to the fourth. That's what our answer would be for C. Let's see, what can I do to change up this problem? Well, let's say we want to add more torque. So let's say that we've got this one acting counterclockwise. Let's say we add one over here. I should use a different color for this. Let's say that on the edge of this one right here, we have acting clockwise 1,500 each. And then, just to make things a little bit extra fun, let's say right in the midpoint of this right here, we have 250 pound each. So now let's take a step back. Think about what we've done. And how about we say we want to find the angle of twist at B, which is about right here. I'm putting right on that edge. Let's think about what's going on. What's going to happen? We have 500 pound inches acting on that edge, twisting it that way. And in the midpoint here, we have 250 pound inches twisting in the opposite direction. And then farther out, we have 1,500 pound inches twisting even more in that direction. So, what's going to happen? Well, we're going to add up. So we're going to have the same thing that we had previously here. Then we're also going to have an additional one right there, plus that one. So just pulling up on my calculator here. Our previous answer for this, which is 4 over. I'll keep it all in radians until the very end. That means, why don't I label these as well? This will be T1, this will be T2, and this one will be T3. Angle of twist. So let's just say we're looking for it at B. So I don't have to label B anymore. So for T1, angle of twist is equal to 2.6 times 10 -7 radians. Once again, we have equation here is phi is equal to TL minus phi G. Trying to make sure that everything can be seen. Why don't I move this just a little bit over? There we go. So let's start out with this smaller one here, the 250 pound inch. Well, our length for this one, if it's being applied in the midpoint, right where this cross section is, and we're looking at B, that would be 12 inches apart. 12 divided by 5. Now, B is not actually, B is right here. It's not necessarily on this larger piece, but rather we're talking about the rod right there. Because if we were talking about, yeah, we're actually talking about, we're talking about right there at the 12 inches. So, as a product of that, it means that this is going to be a comedically small number. pi over 32, yes? Times 12 inches to the fourth times 37 times 10 to the third pizza. So that gives you 3.9 times 10 to the negative 7. And we need to think as well about what direction is this traveling in. You know, you're probably used to, by default, counterclockwise being positive. I will also treat, I'll just write this as a way of explaining for this problem. We'll say that the sum of moments, for the sum of moments, counterclockwise is positive. And so because of that, it means that this number is actually going to be negative. If it's traveling clockwise, it's in the negative direction. So I will add it to the list over here. And see that it actually came out to be a larger number than T1 because the length is that much greater than the 4 inches. Now, let's do T3. We're dealing with 1,500 pound inches. And how far away are we from it? We're all the way on the other side. So 24 inches away. I'll just round this to 4.7 so we can keep one decimal place for everything. Now, if we add all of them together, 1, 2, and 3, so it's 2.6 minus 7. That will give us negative 4.83 times 10 to the negative 6 radians. So that means this would be twisted clockwise 4.83 radians, or in degrees, that would be twisted clockwise, -2.7, but -2.77 degrees.